We are in chapter 5, which is on shear. This is the 41st session overall, and here we discuss some examples on shear center. This block diagram shows the sessions covered in the first 4 chapters. We are now in the 5th session out of 6 sessions in shear. Here we look at examples involving shear center. In the last session, we discussed the theory. We find out the position of the shear center for certain cases. Here we have a section which has 3 vertical portions. The thickness is 8 mm throughout, and the distance between the vertical portions are given. We consider the shear force to be acting downwards, and we'll find the position of the shear center. To start with, we find the moment of inertia of the whole section. The moment of inertia is obtained here. Now we find the vertical forces F1, F2 and F3 in terms of V, the vertical shear force. Consider a small portion in this leg on the top of depth Y, as shown in this figure. The distance from the neutral axis is 25 mm. Then this distance is 25 minus Y. And the distance of the centroid of this portion from the neutral axis is 25 minus Y divided by 2. So for this portion, the statical moment is given as 8Y bracket 25 minus Y by 2, where 8 is the thickness. The statical moment is area into distance. We now find the force in the top half of this leg, F1 divided by 2. Consider a small portion dy, shown in dark shade here. Let the stress acting be tau s on this portion. Then the force will be tau s into E into dy. Tau s varies with y. So integration from 0 to 25 tau s E dy give the force in the top half. Tau s is Vq, right? This is the Q divided by IT. This T and the T in the denominator cancels out. We take V divided by I outside the integral. Here we have written 8V divided by I. Now integration of 25y is 12.5 y square, and integration of y square by 2 is y cube by 6. Substituting y as 25 and I from here, we get F1. We can find F2 in a similar manner. So we consider the force on the top half. The force on the small element is tau s P into dy. Half the length here is 37.5. So we integrate from 0 to 37.5. Q here is 8y bracket 37.5 minus y by 2. Again here we have taken 8 outside. and we find these are the terms within the bracket after integrating. Substituting y as 37.5 and using the value of I, we get F2. Now F1 plus F2 and F3 would be equal to the shear force V. So we can get F3 by subtracting F1 and F2 from V. We have now got the three forces and the moment of the forces about the shear center will be 0. We assume that the shear center is in between F2 and F3. We denote this distance as E. Then F3 into E is equal to F2 80 minus E and F1 140 minus E. Substituting the values of F3, F1 and F2, we get E as 33.13 millimeter. We find the shear center for this cross section. These two horizontal arms are at a distance a by 2 from the neutral axis, and these two horizontal arms are at a distance of 2.5 a from the neutral axis. If a force acts as shown, then the shear flow will create forces as directed in this diagram. The thickness is constant. To start with, we find the moment of inertia of the whole section. So we have found the moment of inertia of this vertical portion about its own axis and added AD square for the horizontal portions. Now let us find the force F1. We consider a small portion at the edge of this horizontal leg. Let the length of the small portion be Z. Then if tau S is the shear stress acting on this element shown in dark, then the force acting on the element will be tau S T into dz. Tau S varies with Z. The length of this arm is A, and to find F1, we integrate tau S T dz from 0 to A. Tau S is V cube by IT. These two T cancels. Q here is area into distance. So the area is ZP and the distance is 2.5 A. We have substituted Q. This portion is constant and we integrate Z dz to get Z square by 2. Substituting A for Z and the IZZ, we get the value of F1. Similarly, we find F2. Again, the force acting on the small element will be tau S dz into T. So F2 is found by integrating tau S T dz from 0 to A. Substituting tau S as VQ by IT. Q here is Z into E into A by 2. This part is constant, so we integrate z dz to get z square by 2. Substituting a for z and I z z, we get F2. Since there is no other vertical forces, the force acting on this vertical portion will be V. All these forces will have zero moment about the shear center. So V into E is equal to F1 into 5A plus F2 into A. Substituting F1 and F2, we get E, which is the distance of the middle of the vertical portion from the shear center. Here we find the shear center for this section. This section is similar to an I-beam, except that the web is not in the center. If we apply a force passing through the shear center as shown, then the shear flow and the corresponding forces in the web and in the flange will be directed as shown. This we have earlier seen when discussing an I section. The horizontal dimensions here are A, B, the height is h, and the thickness is t. We find the moment of inertia. So we first find the moment of inertia of the vertical portion about its own axis, and then add AD square for the horizontal portions. So we have got this expression for IZZ. To find F1, we take a portion from this edge as shown here. This length is Z. The stress acting on this dark element can be found out using Q of this area. The force due to the dark portion will be P into dz into tau s. So the total force F1 can be found by integrating tau s t dz from 0 to p. Tau s is V cube by IT, and Q here is Z into T into H by 2. So substituting the values and integrating, we get this expression. F2 is found in a similar way, and we get a similar expression in terms of A as we obtained in terms of B in F1. So the horizontal force acting would be F1 minus F2. So it is given by this expression. The moment of at the shear center would be 0. So F1 minus F2 into H will be V into E. We get this expression of the distance of the shear center from the middle of the web. With some algebra, we get a compact formula. Here we have another section, and we are required to find out the position of the shear center. If the force is applied at the shear center as shown, then the direction of shear flow and the corresponding forces in the different portions of the section will be as shown. To start with, we find out the moment of inertia of the section. So we find out the moment of inertia of the vertical portions about their own axis. We then add AD square for these two vertical portions. and also these two horizontal portions. So here we have obtained the moment of inertia. Let us now determine the force P1. We consider a portion on the top of depth y. Then the distance from the neutral axis of the top is 3a, and this distance is 3a minus y. The distance of the centroid of the portion from the neutral axis is 6a minus y divided by 2. So Q is area P into y into the distance, which is 6a minus y divided by 2. Consider an element of thickness dy. Then if the shear stress is tau s, then the force acting will be tau s into dy into t. Integrating such forces from 0 to 2a, we get V1. We substitute tau s as Vq divided by It. These two p cancel, and we have substituted q from here. We have taken out Vt divided by I and integrate this portion within the bracket. After integration, we substitute 2a for y and also Izz, and we get V1. Now, in order to find the force F1, we have to know the shear flow at the point B. The shear flow at point B is given as Vq divided by I, where Q is 2a into P into this distance, which is 2a also. Substituting I, we get QP as 0.1754 V divided by A. Consider a section here that is at a distance Z from B. Then the shear flow will be the shear flow at B plus the shear flow due to this portion. Force is given by integration of Q dz from 0 to 2.4a. Can substitute QP from here, and for this portion, capital Q is Z into P into A. Integrating this portion, we get QP into Z, and substituting 2.4a for Z, we get this value. Here we integrate Z dz to get Z square divided by 2. And here we have substituted 2.4a for Z. Adding up, we get F1. Twice V1 plus V2 will make up V. So we can find V2. Now we have all the forces. We can find the position of the shear center. Moment about the shear center will be 0. The vertical forces cause moment in the opposite direction to the horizontal forces. So F1 into 2a is equal to V2 into E, and 2V1 into E plus 2.4a. Substituting the values of F1, V1 and V2, we get E in terms of A. Here we find the shear center for this section. If a load is applied at the shear center as shown, then the shear flow and the corresponding shear forces in the different portions will be directed as shown. We first find out the moment of inertia of the section. So we find out the moment of inertia of these vertical portions about their own axis and add AD square for the horizontal portions. So here we have the moment of inertia. Next we find V1. We take a section at height y from this free end. Then Q is y into P into y divided by 2. The small element force will be tau s into P into dy. To get V1, we integrate from 0 to 2a. We substitute Q. Here the integration is of y square by 2, and so we get y cube by 6. We then substitute 2a and izz to get V1. We find V2. You notice that both these V1 are acting upwards. Here V2, the force acts downwards. The net sum of these three forces will be the force V that acts downwards. So V2 will be larger than V. V2 is equal to V plus 2 V1. Now to find the horizontal force F1, we need the shear stress or shear flow at the point B. Here we have found the shear stress. We use PQ by IT. Q here is 2A into P into A. So we obtain the shear stress at P in terms of P divided by AT. Now consider a section here at a distance Z from this point P. To find the stress here, we have to find the stress tau P and add that to the stress due to this portion. So F1 is found by integrating this term from 0 to 3.2a. Due to tau P, the term that we get is by multiplying this portion into 3.2a into P. Substituting capital Q here to carry out the second integration. Here the other terms are constant. We have integration of z dz, which we integrate as z square by 2. And then we substitute 3.2a for z and also I. So adding up, we get F1. The moment of these forces about the shear center will be 0. These four forces cause moment in one direction, while P2 cause moment in the opposite direction. So we have F1 into 4a plus 2v1 into 3.2a plus e is equal to v2 into e. Substituting F1, v1 and v2, we get the value of e in terms of a. We find the formula for IZZ for an inclined section. This section has thickness T and this length is B. It is inclined at an angle beta as shown. Then X here is P divided by cos 90 minus beta or T divided by sin beta. The vertical height h is b sin beta. Izz of the inclined portion about the base is x h cubed by 12 plus ad squared, which is x h into h by 2 squared. We substitute x and h in this equation. X is t divided by sin beta and h is b sin beta, from which we get Izz is equal to P b cube sine square beta divided by 3. So this is the formula we use. We can find the Izz of this inclined portion. Izz of the whole is Izz of this vertical portion and Izz of the two inclined portions. If a load is applied vertically at the shear center, then the direction of shear flow and the corresponding forces in the different portions will be as shown. We now find out the force F1 in terms of V. Consider a portion from the free edge. So here a portion is taken, its length is S. Then the distance of the centroid of the portion from the neutral axis would be S divided by 2 into sine 40. If tau S is the shear stress corresponding to this element of ds, then the force will be ds into P into tau S. So we can find F1 by integrating tau S T ds from 0 to 89, since 89 is the length of this inclined portion. Tau S is VQ by IT, where we have found out Q earlier. We substitute Q to get F1. The force F1 can be resolved into vertical and horizontal components. The net force acting on this section vertically would be V downwards. The vertical components of these two forces act upwards. So F2 has to be greater than V. So we find F2 here, V plus twice the vertical component of F1. We can find the position of the shear center in two different ways. We can resolve the force F1 and F3 at these two corners. Then the horizontal forces F1H and F3H will create a moment. F1V and F3V aligns with F2 and they create a moment. These two moments will cancel each other. So here we have F1H into this distance is equal to F2 into E minus 2 F1 into E, from which we get value of E. Another way to resolve the forces is shown in this diagram. These two forces passes through the point A. AL is 68.18, which can be obtained from this diagram. If we resolve the two forces in horizontal and vertical directions, then the horizontal directions will cancel out. The vertical direction, the force would be twice F1V. The vertical force F2 causes a moment about the shear center, and 2 F1V causes a moment about the shear center. So we equate these two moments to get the value of E. Here we have another cross section which has inclined legs. We'll find out the position of the shear center of this cross section. If a force is applied at the shear center as shown, then the direction of the shear flow and the corresponding forces in the sections will be as shown in this diagram. Here we do not use the formula that we have earlier found out for finding out moment of inertia of inclined legs. Theta here is 50 degrees, and we can find x in terms of P. P divided by x is cos theta, and we find x. We find out moment of inertia of the whole section. This is the moment of inertia of the vertical portion. Here we use x into 70 cubed by 12 into 2 as the moment of inertia of the inclined portions, plus 80 square for the inclined portion. So we obtain the total moment of inertia. Next, we'll find out the force F1. Consider a portion from the free edge. Let the length of the portion be S. Then the distance of the edge from the neutral axis is 50 plus 70, that is 120. The vertical distance is 0.64 s. So this distance is 120 minus 0.64 s. So the distance of the centroid of this portion from the neutral axis is given as 120 minus half of this value into s. So we get q as t into s into this distance, which is 120 minus half of 0.643. The force acting on an element would be tau s into ds into t. So the force acting on this whole length, which is 108.91, is tau s t ds integration from 0 to 108.91. We can write tau s as vq by it, where we have earlier obtained q. We substitute and we take out Vt divided by I. Integrating, we get an expression in S square and S cube. We then substitute this value 108.91 for S, and we get F1 in terms of Vp divided by I. This angle is 50 degrees, so F1 sine 50 degrees would give F1H, and F1 cos 50 degrees would give F1V. We can again resolve the forces in two different ways to find the distance of the shear center. Here we have resolved F1 and F3 at the corners. Then the horizontal forces create a couple and the vertical forces align with F2. The sum of all these vertical forces has to be V. So F1H into 100 be equal to V into E, as we have here. We substitute the value of F1H, get the value of E. Another way to solve the problem is to find the resultant of these two inclined forces. We resolve the inclined forces at this point. The horizontal forces cancel out and we are left with twice F1V. We can find the distance KL from geometry. This angle is 50 degrees and this distance is 50. We get KL as 59.59 millimeter. Then 2 F1V into 59.59 minus E is equal to F2 into E, where F2 is V minus 2 F1V. So we get this equation substituting F1V, we get the value of V.